Hello, everyone. I'll be talking about the hip exoskeleton modeling that I did for my final project. So basically, this is the hip exoskeleton mathematical modeling structure, where as you can see the electrical component of the model and the mechanical component, and the gears which represent the transmission to the wearable structure. This is the overall modeling structure, which shows the quasi-direct drive, the transmission, and the wearable structure. As you can see, this is the electrical part of the model and the mechanical part showing the structure of the model and the transmission and the wearable structure. So basically, the electrical part has the voltage and the resistance and the inductance, and this is the governing equation of it. And the aim is to have higher torque, and that is why the gear is there to amplify it and lower speed of the model, such that the assistive torque will be much more prominent for the human that will need it. Here is the derivation of the bandwidth. Here is the derivation of the bandwidth showing the output-input transfer function of it, where this is the back EMF, here is the voltage of the model, the current applied, the torque by the model, and the assistive torque. And this is the functions that we are interested in. These are constant based on the Laplace transformation. And here's the bandwidth simulate control block diagram. And here's the simulink control bandwidth, showing the PID motor controller, the mechanical part, the gear, the torque sensor, and the output, and of course the feedback. For the drivability, this is the derivation of drivability, showing the increase in torque and the reduction in the speed of the model. And to compare the series and elastic quasi-direct drive actuator, for series elastic actuator, the back-drivability is medium. In QDD, the back-drivability is really high because of a low resistive torque. But in the bandwidth of SEA is low compared to quasi-direct drive. And the aim is that you don't want any model that you are creating to be bulky. You want the people that are wearing it to be able to wear it comfortably. And what we did was to create a Simulink control block for our work, in which we input this parameter to see how it's going to react. At the end of the day, I was able to get a very high value for the bandwidth for QDD and a very considerable size bandwidth for the SEA. Likewise, for the back-drivability, you can see that the back-drivability of the QDD is very low when compared to the SEA. So overall, QDD has better performance. So in this class, I learned a lot. I was able to learn so much about the work. I was able to learn about PID control. I was able to learn about model. I was able to learn about Arduino, and also I learned about the pneumatic actuators and the hydraulic actuators, which can be used for soft exoskeleton. The most exciting thing is that I learned about the back-drivability and the bandwidth, which is very, very important, which is an important component in sizing an actuator. And because Practically, you can do this work practically, but it's still it's always good by if when you can actually check check it theoretically by doing simulation in Simulink. I hope this helped.